Make sure your name is on those chapter 1 questions, numbers 6 and 10, and then pass things to the right-hand side as always. So name on it, to the right side. Remember that I remind you that the web-assigned problems are due tomorrow at 12:20 p.m., even though we don't have class. Okay? Recall that. All right, chapter 1, questions 6 and 10. Make sure your name is on them. Please pass them to the right. See it now.
Should I just give it back to
Just
you?
put your name on it, that's fine.
No. Here, 6.
Pass those down.
Thank you.
Just your name is fine, you don't have to put the date or the period number or anything like that. It all stays together in the same pot. All right. Before we begin today, and now that we are past the first exam and starting to make a transition through the class, I have for you the following. Something you may have been wondering for yourselves, by the way, as we began this class over the first couple of weeks.
Prior to the beginning.
Okay, over the course of the first couple of weeks here, you may have been asking yourself the following question: how do you survive and thrive in a physics class? Well, it turns out that there's actually lots of resources available to you. I'm going to briefly describe what is in fact available to you in this manner. Okay, first and foremost, some of you are already doing this, but not nearly enough of you perhaps are doing so. You should always come asking for help during lunchtime tutoring if you're struggling with something. So I encourage you to start the homework always as soon as you possibly can, including the web assignment, such that if you do have any questions, you can then come ask me for help during lunchtime tutoring. As some of you have discovered, I'm usually here in my room 99% of the time during lunch, helping students out with homework problems and so forth. So if you find yourself struggling with something, don't hesitate to come ask me for help. I'm also available sometimes during 7th period, but you've got to check with me ahead of time. You have to make an appointment. I'm usually available at the beginning of 7th period if necessary. Okay, secondly, there used to be a companion website to the textbook that was pretty good, but that companion website is no longer there at the moment. I suspect that what they are doing is actually rebuilding the website. As soon as it comes back online, assuming it does, then I'll go ahead and link it on Schoology. But that website, at least it used to, had a number of additional outside study aids and resources for students to take a look at. I would never refer to the website in any way, but it's just an online resource that's available to you. As I said, as soon as it comes back online, I'll link it on Schoology. And then also on Schoology, I have a folder called Useful Links, where I've started already to bookmark some additional resources for you. I'll be doing a lot more of that over the course of the next week or so. These are all, once again, just online additional study aids and resources. I encourage you to take a look. And fourth, what you're probably beginning to realize is that the way that you prepare for an exam in physics class is by practicing. For example, by practicing solving problems. This type of strategy will become more and more important as we get further and further into the course. So as an aid for test preparation, you may want to consider purchasing one of these. This is an example of what is called a problem solver. What a problem solver, all that it is literally one problem after another with the complete solution there for you. So something like this is very good for test prep, not necessarily for doing homework, but for test prep, in the sense that you could just simply get a lot more practice in. So you practice solving problems then in order to prepare for exams. If you've got the solution right in front of you, then of course that's a good study aid. This particular book, the information is on the handout. It's pretty easy to obtain. It's part of a series of problem solvers by the same publisher. It's called Schoen's Outlines, and this is the one for introductory physics. It's called 3,000 Solved Problems in Physics. You can find this pretty easily at Amazon. You can find it at college bookstores. It retails brand new for about 30 bucks. But if you're industrious, you can probably find them on eBay for 10 or 15 bucks. There are usually some copies for auction. I'll leave this here on my desk during the break today, or at the end of the period. You can take a look at it if you wish. Okay, turn the paper over. Okay, some of you may have already been doing this, and that's perfectly fine, but I do encourage you to work together with a small study group when it comes to sitting down and solving problems together. That's a very effective means of learning. If you find yourself kind of floundering in isolation, you want to try and rectify that as quickly as possible. Get a study buddy or two. That's a really effective means of learning in a technical class such as this. Now, there is a little bit of a warning associated with that. What that doesn't mean, of course, is that you can simply, say, copy each other's homework right before class and then turn it in. That's not working legitimately with a study buddy. That's cheating, and if I do catch you doing that, then I will report you to Dean Howard. So when I say working with a study buddy, you are doing so legitimately, working out the problems together as you go. That's perfectly fine. Don't struggle in isolation. Get a friend or two and work in that way throughout the entire course. And then lastly, this is kind of if all else fails and you're kind of at the end of your rope. If you think you might have to go the route of finding a private tutor, the best place to start is actually the UCLA Physics Department, because they have a pretty comprehensive list of tutors in the West LA area, such that you can readily contact someone if necessary. But that's really only as a last resort. First and foremost, you should always come ask me for help if you're struggling with something. If you find yourself at the end of your rope and you have to go that route, start by looking for a tutor and information. Okay, are there any questions? Okay, good. Go ahead and go to the side, please. Pick out your notes. All right, essentially what we have done here over the first couple of weeks of class with this opening unit is I've given you a very highly condensed version, if you will, of about 2,000 years of history, the history with regards to the study of celestial motion. That history kind of culminates with the discovery of Kepler's laws of planetary motion. So, we've studied thus far the history of the study of celestial motion. Culminating with the discovery of Kepler's laws of planetary motion. Once again, this was roughly 2,000 years of history stuffed into the first couple of weeks of class. While all that was going on, however, kind of in parallel at the same time, an additional type of motion was being studied, and this had to do with motion near the Earth's surface. So while this was going on, in this stretch of history, motion near the Earth's surface was also being examined. And essentially everything that the ancient Greeks knew about motion near the Earth's surface can be summarized into two simple statements. Everything the ancient Greeks thought about such motion summarized into two simple statements. The first of those statements is as follows. According to the ancient Greeks, heavier objects fall faster than lighter objects. Now, if you just observe the behavior of the falling objects in the natural world, this statement seems confirmed. For example, let's say that I have two objects. I'm going to have a relatively light object, say this piece of paper, and a heavy object, this white out dispenser. And then all I'm going to simply do is hold them here at the same height above the floor and let go of them at the same time. And exactly as you would expect, the heavier object hits the ground first. So based upon observations like this, it's very easy to reach this conclusion. Now, as I previously have mentioned, the ancient Greeks are given a lot of credit when it comes to the beginnings of science. They were the first culture, once again, to begin to view the world as something that could be understood as a mechanism. But when it comes to the scientific method, the ancient Greeks, it turned out, actually made a lot of mistakes. They missed a very crucial step of the scientific method, and that step was experimentation. The ancient Greeks never did any experiments. They thought it was good enough to just observe what was going on around them in the natural world, and then draw conclusions from those observations. And as you just saw, it's very easy to reach, for example, this conclusion here. However, if I conduct a very simple experiment, I can immediately show that there's actually something wrong with this statement. Notice that I just crumpled up the same piece of paper. It's exactly the same as it was before, it weighs the same. But now watch what happens when I take the two objects here, hold them at the same height above the floor, and then let go of them. Now they appear to hit the ground at the same time. An experiment like this doesn't definitively prove that that statement is incorrect, but it does at the very least show that there is something wrong with it. And then secondly, once again, with regards to motion near the Earth's surface, according to the ancient Greeks. According to the ancient Greeks, all moving objects eventually come to rest. It was thought by the ancient Greeks that there is something special about being at rest. They referred to it as an object's natural state. And naturally, an object wants to return to its natural state. That is, all moving objects eventually come to rest. So a state of rest was thought to be the object's natural state. That's how they refer to it. Now, hopefully you're aware that both of these statements are in fact incorrect, but they were experimentally shown to be incorrect by a very important figure in the history of science. And this is now once again into the early 17th century with the Italian Galileo Galilei. So now we get to the 17th century. Galileo Galilei, or we just refer to him as Galileo for short, is a very important figure in the history of science. One of the things that he did, as we'll begin to see over the course of the next couple of weeks, is that he experimentally shows that these statements are incorrect. However, Galileo makes a number of other contributions. Most of you are probably aware, at least to some degree, of the contributions that Galileo made to astronomy. So actually, let me begin my description here of Galileo with that. First, describe his contributions to astronomy. Okay, contrary to popular belief, Galileo did not invent the telescope. Okay, the reason why we understand that is because it turns out the telescope was invented by a Dutch lens maker named Hans Liffery. And Hans Liffery himself actually probably didn't invent or discover the telescope. It was probably one of his children playing around with lenses in his laboratory. For example, let's say you take two lenses, one that is shaped like this, and another that is shaped like this. If you take the two lenses and then place them together, and then look through the lenses, say like so, and if you get the positioning of the lenses just right, you could actually greatly magnify images that are objects that are distant in the room. So for example, if I position these lenses like so, I could actually see now very clearly and magnified. I can see the posters, for example, on the back wall. This was probably a serendipitous discovery by one of Liffery's kids. If you take the lenses and just look through them in this manner, well, what one of those children actually discovered is the refracting telescope. Now you can see this for yourself. I'm going to just pass the lenses around to you. And what I want you to do when the lenses come to you is hold them exactly as I did, and then say pick a distant object on the wall or something like that, and take a look at its image and its magnifying. When Galileo first heard about the telescope, he figured out very quickly how it had to work, and he then went about building several of his own. And in 1609, he becomes basically the first person in history to use the telescope to look at celestial objects. And with his observations, even with as crude as his telescopes were, he discovers direct observational proof that Copernicus is correct. The sun is the center of the solar system, and the geocentric theory of the universe is very quickly disproved. As we'll see, he's the first person to use the telescope to look at celestial objects. Even with his relatively crude telescopes, his observations lead directly to disproving, once and for all, the geocentric theory of the universe. His observations, as we'll see, I'll show you some slides in a little while, disprove the geocentric theory. And let me give you a brief description of his observations, and I'll show you some slides that go along with it. Okay, first and foremost, you use the telescope to look at the moon. And when you look at the moon, even under relatively low-power telescopes, and even if they're very crude, you immediately begin to recognize what can't be anything other than geographical features. If you look at the moon with a relatively low-power telescope, or even with binoculars for that matter, you can very easily see that what you're obviously looking at are mountains, valleys, craters, and so on. Galileo realized immediately what it was that he was seeing. And then therefore, for the first time in history, we now begin to think of the moon as a place, rather than some disk in the sky, for example, that's reflecting the sun's light. When we look at the moon, you immediately recognize geographical features. For example, he immediately saw that when he was looking at mountains, valleys, etc. So then all of a sudden now we begin to think of the moon as a place. And then secondly, he's lucky he didn't go blind in doing this, but he looked at the sun. Now, how would he do that? Well, he would kind of wait for the right moment. Like, for example, when there's a little bit of fog passing in front of the sun's disk. And how many of you have tried this for yourself? You've looked briefly at the sun's disk like so through the fog. Don't do that, by the way. That's not a good idea. Because if the clouds part a little bit, you can go blind almost instantly if you look directly at the sun. So what Galileo would literally do is he would wait for the right moment when the fog was covering up the sun's disk, and then get out his telescope really fast and then look at the sun. Don't do that. A little bit later on, by the way, at the end of the period today, we'll use my telescope here, which is an example, by the way, of what is called a reflecting telescope. It doesn't use its lenses. Instead, what it uses at the bottom of the telescope is a mirror. But we'll actually be able to safely look at the sun through this telescope by means of this filter that is here at the top of the tube. This filter right here blocks literally more than 99.9% of the sun's light that is striking the telescope, thereby making it safe to look at the sun. And when we look at the sun at the end of the period, like Galileo did 400 years ago, you're going to be able to see sunspots. Now, 400 years ago, when he saw sunspots, he had no idea what it was that he was looking at. Our understanding of sunspots didn't come until much later. But what sunspots actually are magnetic storms on the surface of the sun. And when you look at the sunspots at the end of the period today, just keep in mind the following. Each of the sunspots that you're going to see are actually several times larger than the Earth. The sun is pretty large. It's about 800,000 miles across or so, something like that. So when you see sunspots at the end of the period today, just keep that in mind, that they're actually larger than the Earth itself. And then third, you look at the planet Saturn. Now when you look at the planet Saturn through a relatively crude, low-power telescope, even though Saturn is way out there in the solar system, instead of being a point of light in the sky, it noticeably shows as a disk. And then immediately next to that disk, Galileo described what he thought were meteors, some sort of objects associated with the planet itself. He didn't understand what it was that he was looking at the time, but what he was actually seeing were Saturn's rings. That understanding of what Saturn's rings are didn't come until a little bit later. But suffice it to say, he was the first person to see it. So Saturn's rings. Okay, but it's really the last two observations that he makes that are the most important of all. Two very important observations. First has to do with Jupiter. Now, like Saturn, when you look at Jupiter through a telescope, it shows up very noticeably as a disk. Jupiter's pretty big, and it's a lot closer to the sun, it turns out, than the planet Saturn is. So even with a relatively crude, low-power telescope, you can see the planet very noticeably as a disk. And then you could actually see what we now today understand are the cloud bands of the planet itself. They appear as a series of stripes going across, like so. Galileo didn't understand the nature of what it was that he was seeing, but he did make an educated guess, and he thought correctly that what he was seeing are once again some sort of geographical features. So like the moon, we now start to think of Jupiter, for example, as a place. In addition to the cloud bands of the planet itself, he was also the first person to see the famous Great Red Spot. We understand today exactly what the Great Red Spot is. It's actually a gigantic hurricane. It's a hurricane 4 times larger than the Earth. He was the first person to see it over 400 years ago. But a little bit more importantly, surrounding the planet in a line parallel to the equator, are 4 spots of light. So, and even over the course of just a couple of hours, if you watch those spots of light, they very noticeably change position. And then it's certainly noticeable over the course of successive nights. So let's say, for example, that you look at the planet Jupiter one night, and you see that. And then you look at it the next night. And once again, see the planet, the cloud bands, and so forth. But you'll see that the positioning of these 4 spots of light have noticeably changed. Galileo realized very quickly that what he was seeing were objects that were orbiting the planet. These are now the 4 major moons of Jupiter, which are now named in his honor. They are referred to as the Galilean moons. So we observe, we now call today, the Galilean moons. The reason why this discovery is so important is because it's the first direct observational evidence of motion in the sky that is definitely not centered on Earth. First observational evidence, motion in the sky. That is not centered on the Earth. Now, as convincing as this observation is, the real clincher when it comes to disproving the geocentric theory of the universe has to do with the planet Venus. Now, when you look at the planet Venus over the course of weeks and into months, you see very noticeably 2 changes associated with the planet. Number one, like the moon, the planet Venus actually goes through a set of phases. And in addition to that, it also changes its apparent size in the telescope as you look at it over the course of weeks and months. It changes its apparent size. Please be quiet. Here's what I mean by that. Let's say that you look at the planet, say, just after sunset. And what you will see then over the course of weeks and into months is the following. You'll first observe the planet, and you'll see it small in the telescope, and it'll appear as a gibbous. So, but a couple of weeks after that, the planet will be bigger through the telescope, and it'll appear as a quarter. A couple of weeks after that, it'll be bigger still, and it will appear as a crescent. And then there will actually be a period of time where you won't be able to see it at all, a couple of weeks. And then a couple of weeks later, instead of seeing the planet near sunset, you would actually see it near sunrise. And then when you look at the planet then through a telescope, you'll see it as a crescent again, enlarged. And in this case, the crescent will be on the other side. Like so. A few weeks after that, it will be smaller, it appears a quarter. You'll notice it's reversed from what I drew over here earlier. A few weeks after that, it will be smaller still, and appears a gibbous once again. Yes. Galileo realizes that the only explanation for this is that the planet Venus has to be orbiting the sun closer than the Earth is. I'll show you this with my slides in a few minutes as to why this is. Galileo does make this realization. The only explanation is that Venus orbits the sun closer than the Earth does. It is really this observation right here that is the first direct observational evidence that Copernicus is correct. All of the planets, including the Earth or the Sun, this disproves the geocentric theory of the universe. This observation disproves geocentric theory. Now, how does this observation make this proof? I'll show you with some slides in just a few moments. Ryan, what's your question?
I understand how this proves Copernicus' theory, but wouldn't it also support Tycho Brahe's?
No, it doesn't. And the reason why it doesn't, because at the same time that Galileo was making these observations, earlier Copernicus had already done his work, calculating out the sidereal periods of the planets, assuming that when a planet is closer to the sun, it moves faster in its orbit, culminating then eventually with Kepler's laws of planetary motion. Kepler's laws of planetary motion were discovered by Kepler at basically the same time that Galileo was making these observations. So the two kind of work together at the same time. It's like you have the math of Kepler's laws, which mathematically explain the orbits of the planets about the sun, and then backing that up observationally are these observations that Galileo made through the telescope. So you have observational evidence, and you have mathematical evidence as well, and they work together to disprove the geocentric theory of the universe. That's the basic idea. In other words, there's no other possible explanation for these phenomena. The only explanation is that all the planets, including the Earth, orbit the sun. That's the easiest way of picturing it. So you have very powerful evidence, essentially, kind of twofold, mathematically with Kepler's laws, and observationally now with the telescope, that basically disprove the geocentric theory. And of course, everything that we have seen in the successive 400 years disproves the geocentric theory. But this is kind of like the final nail in the coffin, if you will, Galileo's discoveries. Once again, it's a little bit difficult to picture why this is. That is, why the only possibility is that Venus is orbiting the sun closer to the Earth is. So let me show you some slides. Okay, first of all, here's a painting of Galileo when he was an old man. Okay, take a look at the dates there. He was born in 1564 and died in 1642. 1564, by the way, is about 20 years or so after the death of Copernicus. So Galileo, yes, comes after Copernicus. It is important for you to know the history of exactly what happened to Galileo. I'll explain that to you at a later date. For now, yes, he was eventually tried and convicted by the Catholic Church for his support of the Copernican system. And as I said, through the telescope, we now have the first direct observations to support the Copernican theory of the universe. Before I go through Galileo's observations, let me also briefly mention this man who lived at the same time. This is an Italian monk named Giordano Bruno. Bruno was not a mathematician or an astronomer, he was just a theologian. However, he was a firm believer as well in the Copernican solar system. Unlike Galileo, who was very well connected politically, Bruno was not. And when Bruno was labeled as a heretic, he was ultimately tried and convicted, and he was burnt at the stake in Rome in the year 1600. How Galileo managed to escape the same fate, I'll get to a little bit later on, but for now, Bruno, it turns out, was not so lucky. Bruno, by the way, was also the first person, just as a lucky guess, if you will, to hypothesize the existence of planets orbiting other stars. As you might guess, the Catholic Church didn't think too kindly about that either. This right here is a statue of Bruno that is erected at the spot where he was executed. This is in Rome in 1889. That's actually when the statue itself was erected. I took this picture. Okay, getting back to Galileo. Galileo's primitive telescopes actually survive to this day. They're housed in the Museum of the History of Science in Florence, Italy. Galileo spent most of his adult life in Venice and in Florence, Italy. This right here was one of his first telescopes. It was about this long or so, something like that. It was able to magnify images by about 9 times. We'll describe, by the way, how telescopes work in detail later on in the second semester. These right here are some of the later telescopes that he built. The best that he was able to do throughout his life was to build a telescope that was able to magnify images by about 30 times. And then we get to his sketches. This right here is the sketch of the first quarter moon as you would see it through a relatively low-power telescope. Somewhat annoyingly, what Galileo kind of had a habit of doing in his sketches was exaggerate just the clarity and detail of the geographical features. When you look at first quarter moon, for example, through a telescope, there is a crater approximately right there on the surface of the moon, but it's not nearly that big as Galileo drew it. He basically exaggerated his drawings for clarity. Okay, here's some close-ups of mountains and valleys and craters and so forth. You would be able to see this stuff pretty clearly with a relatively higher power telescope, such as some of the later things that Galileo made and had at his disposal. Then here are some simple sketches of the motions of the Galilean moons, as we now call them today, over the course of successive nights as those moons orbit the planet Jupiter. Once again, this is first direct observational evidence of motion in the sky that is not centered on the Earth. We know a lot today, by the way, about these 4 moons. They're very fascinating places. They're called Io, Europa, Ganymede, and Callisto. And then here are some of his simple sketches of Saturn's rings. Remember, once again, he had no idea what it was he was seeing when he was looking at Saturn through the telescope. Our understanding of the rings came a little bit later. Here's a nice drawing showing some sunspots. Sunspot groupings that you see there on the sun's disk are a little bit larger than the ones that are actually on the sun right now, and I'll show you those at the end of the period, but very easily each one of those sunspot groupings there is much larger than the Earth itself. Okay, now we get to this all-important observation with regards to the planet Venus. Here's his original sketches showing, for example, the change in the apparent size of the planet and its phase as it goes from being a gibbous to a crescent. Once again, how does this definitively show that Venus is orbiting the Sun closer than the Earth is? Well, let me show you kind of like a more modern version of these sketches. Take a look at this series of photographs. So imagine, for example, taking a look at the planet Venus when it's right here as a crescent. You would see it near sunrise. And then you would see it as being quite large through your telescope. And then as you watch it over the course of successive weeks and so on, you'll see it getting smaller and smaller in the field of view, and you'll see more and more of the gibbous phase. Notice it very obviously in this form of a composite photograph, that it very obviously looks like that Venus is moving around something else. That something else is obviously the Sun. Here's a graphic that depicts it for us very nicely. Now, just for clarity, let's assume that the Earth is not moving here on this diagram, just to make the situation easy to picture. And let's say if you begin by looking at the planet Venus when it's here in its orbit about the sun, you would then see it through the telescope as it gives phase. Notice that it's pretty far from the Earth when it's there in its orbit, so it's going to be small in the telescope. And then, as Venus begins to catch up with us, remember that Venus being closer to the sun moves faster in its orbit. A few weeks after this, we would see it as being closer to us like so, and you would see it as a quarter. A few weeks after that, it's closer still, so it appears larger in the telescope, and then it appears as a crescent. And then there's basically a period of time when the planet is right here at inferior conjunction, where you're not going to be able to see it at all, because the sun's in the way. So then a couple of weeks after that, you'll be able to see it at sunrise as a crescent, and eventually as a quarter, and as a gibbous, and so on. Once again, the only explanation for all of this is that Venus orbits the sun. So here it goes. Okay? All right, let's take a short break right here.
Yeah, he said it's a hurricane. It's like 40 years
I mean, like, I knew I needed to find it X squared, I knew it had to be more about the last each other, I just remember. Other than that, I did it pretty well. You took a point off my test result. I mean, I just used too lazy to calculate it. So she gave the test factor, it will go up, but then calculate it other ways, because I did so bad. And then I just calculated my grade. Don't worry about it. And I just gave the test here. And I hit it. Oh, so it's like that. You're right? Yeah.
You're in the
Why did I test it? You did. I
got it.
And I get a minus point? Yes, no, I already gave it. Where did you guys interview with?
US.
I mean last year. So like, for this company, I got a 77 that's for yeah. I got a 6. Did you guys get minus? I got a show.
Honestly, it's just the test. We went over it. Who else was good? Do I remember this Christmas?
I bet you.
I'm very
watching.
You guys are good.
I was challenged. You were in a concert. I was one of nature.
Wow. I can't believe I didn't recognize people who were in honors math. Yeah, I know.
Do you remember recommending? I don't know. Why?
Yeah,
Well,
Mitchell.
eventually getting a meeting.
Yeah, like, yeah, I got it.
No, he like,
I feel like a Peter yet.
waivers. I think so, like, yeah.
Yeah, Mitchell wasn't supposed to have that.
He was gonna waiver it, but then he got regular, not regular high school cal with, doctor, first period, and then they randomly switched it so that he's service work.
Well, you're in the right place here.
You know, it's Mitchell's birthday.
Yeah, I'm thinking.
I know, and I was like.
Oh, you're drinking?
Do you see his mermaid balloon?
I have a couple of students in AP this year. They're like,
Yes,
Yeah, I was like, sorry dude, but I'm on a diet, and I don't feel like giving it.
and I'll put this, the difference between regular and honors is kind of like.
Yeah.
Oh,
You went to
I
the
just
same
fell
summer
asleep
school.
so
Yeah.
hard when he said we have a break. So I put my head down. I fell asleep
It's a little more.
I have trouble falling
because
asleep.
I would like sleep and I'd wake up and like, oh, I was gonna sleep, and then I'd fall
You're gonna get the
asleep.
exact same stuff as the APs are doing, it's just, it's slower.
Like more time to study.
there,
During
which
the
is
break.
first.
You ever heard my question?
So the students.
You're right, ease you guys
Support
into
Tycho
it.
Brahe.
These last couple of weeks is also ease everything.
That's not what Brahe is as well, so.
They, no, they don't, but I give them a very condensed version of what I gave you guys.
That's amazing.
They get a very condensed version. Because that history is very important.
I'm not worried that you
Do we still cover the same amount of material as they do?
No, you cover also some different.
What did you think?
A lot of the stuff will be the same.
I was like.
So like if you talk to your friends that are in AP, you will recognize what you're doing in each class. But there are other things that they do that you guys don't, and vice versa.
Do students that take honors quizzes and then do pretty well?
Oh, yeah. I think I have like 5 minutes.
I want to go home soon, but I
They usually have
Amazing.
5 or 6 minutes.
Do you still at 826?
That's the first day.
Huh?
First day this week.
What? I sound so
I'm just kidding.
I can't do it.
There's not a huge difference between the two. The difference is, number one, you
And I already
so you guys
have
get
100
hours.
hours.
You do a little bit
From
of
that?
algebra
Oh my God.
on a regular does not, it's algebra based. You guys cover
Takes a long
virtually
time
the
to
exact
get
same
hours.
material. A
There
lot of the
for
lectures are just completely
3
identical.
hours. How often
But
do
you
you go?
guys get harder tests, harder problems, just a few more things that we do in this class. You know,
When I
in terms
started
of concepts
sophomore
and
or
topics that we
freshman
don't
year.
do at the regular level. But there's not a huge difference.
So I'd back up
The big
like
difference is
50 hours, 30 hours.
And that's the way it should be.
No, have you seen what I
I'm doing.
No.
All right, let me go ahead and move on. Please take your seats. Okay, by the way, one thing that I forgot to mention a little while ago while going through earlier in today's lecture was how the ancient Greeks were able to reach the conclusion very simply that all moving objects eventually come to rest. That's the second statement, if you will, regarding motion in your surface. I just briefly forgot to mention how it is that they arrived at that conclusion. Remember that they just based everything upon observations. So if you observe the behavior of moving objects around you, this seems confirmed. You take an object and drop it, it comes to rest. You take an object and toss it through space, it comes to rest. You take an object and say slide it horizontally across the desk, it comes to rest. So once again, it's very easy to reach that conclusion. In this case, all moving objects eventually come to rest by just observing what goes on in the world around you. But then we come to, once again, Galileo. As I mentioned, Galileo is kind of like this crucial figure, if you will, in the history of science, and not just for his astronomical contributions that I have already previously mentioned. We also think of Galileo as like the world's first scientist, but in the true modern sense of the word. Because Galileo is given a lot of credit for the development of the scientific method. Along with a couple of other people at the same time, Galileo is really one of the first people to do comprehensive experiments, and then use his experimental results to either prove or support or disprove hypotheses. So he's given a lot of credit for the development of the scientific method for that reason. Now, in order to understand, however, exactly what it was that Galileo did experimentally, we have to start to go through some mathematical background. And as I go through this mathematical background, you're going to see it entirely using modern notation. So I'm not going to use the notation that Galileo used 400 years ago. It's very archaic. What you're going to see from this point forward is done now in a modern sense. We have to go through and refer to it. Okay, first of all, what is a vector? Well, a vector is any quantity that has two things associated with it. A size, typically called a magnitude, and a direction. Any quantity, size, typically called magnitude, and direction. Now perhaps the simplest example of a vector quantity would be position. Let's say that you were going to describe the position of me in this room. You would basically have to describe two things. First of all, you would have to set up some sort of coordinate system. So imagine that this room is a coordinate system of some sort, and then we'll say the origin is the door. And then my position relative to the origin would have to be stated in the following way. You would first of all have to say how far I am from the door, say 6 feet. That would be the magnitude. But you would also have to say the direction as well. So according to you guys, I'm standing to the right-hand side of the door, so you would describe my position as 6 feet to the right-hand side of the door. you just describe the vector quantity because it has a magnitude, 6 feet, and a direction to the right-hand side. That's a little bit different from what is called a scalar quantity. A scalar quantity is any quantity that just has magnitude, no direction. A nice physical example of a scalar quantity would be temperature. You would say, for example, that the temperature in this room is 75 degrees Fahrenheit. You would not say that the temperature in this room is 75 degrees Fahrenheit to the right. In other words, there's no direction associated with temperature, therefore it's a scalar quantity. Ordinary numbers, positive numbers, negative numbers that you've been manipulating since kindergarten and first grade, those are scalars as well. You weren't told this at the time, but you learn mathematics, how you basically manipulate numbers as scalars, because they have no directions associated with them. They're just assigned with specific numbers, that is, they just have a magnitude. So ordinary numbers are scalar quantities. Here, however, you start to learn the basics of vector mathematics. There is a specific notation that we use to denote a vector. First of all, we always represent a vector as an arrow, like so. And then let's say that we assign a variable to this quantity. Let's just call it the variable a. To denote that a is in fact a vector, you're going to see me draw this little symbol above it myself. This specifically means that a is a vector quantity. However, in textbooks, including your own, it's done a little bit differently. Vector quantities in textbooks are always in bold type. So you're going to see the letter A in bold type. When I write it on the board, however, you'll see me draw the arrow itself. So in texts, including your own, vectors are in bold type. And then there are two things associated with this vector. First of all, you have the size of it, its magnitude. Think of that as just the length of the arrow. The magnitude of the vector A is just the letter A by itself and without the vector symbol above. The way that you'll see it in the textbook is that it's just in normal type. So when you see the letter A in bold, it means it's a vector. If you see it in normal type, then it's just the magnitude of the vector. It's the size of that arrow. And then the second thing about this arrow, about this vector, is that there's a direction associated with it. Say with respect to the positive x-axis like so, the vector itself forms an angle. Just call it theta here generically. Angle theta just indicates direction. And then at this point, you just start to learn the basic mathematical operations of vectors. How do you add vectors together? How do you multiply vectors by numbers, and so on. You start to learn this in both 1 and 2 dimensions. And it's basically, by the way, at this point, where from this point in the class all the way until the end of the year, you're going to see me do tons of examples. I always do examples the same way in this class. What I do is I project the example up here to the screen. Like so. I give you a couple of minutes to copy down the problem, the example, into your notes, and then I'll go through the solution. Every now and then, I'll have you guys actually try the examples, but for now, for the most part, including today, I will go through the solution here on the board. Take a moment here to write it down into your notes. Notice what's being described here in this problem as you start to read it are position vectors. You have to add them together. So what's being depicted here in this problem is one-dimensional vector addition. All right, so here's how we begin to break the problem down. Once again, this is one-dimensional vector addition being described. Okay, we first of all have the person starting at the origin, initially pressed, and then the person walks 10 meters to the right-hand side. So that's the first vector. Let's just call it A. So A is equal to 10 meters to the right. Now notice that as I wrote this down, I had to indicate two things. Magnitude, that's 10 meters, and direction, to the right-hand side. However, writing the phrase to the right is considered somewhat redundant. Let's just consider the motion of this person to take place along a number line. The right-hand side is the positive direction, the left-hand side, which is saying is the negative direction. So instead of saying the phrase to the right, let's just write it as plus 10 meters. It's perfectly fine. And then secondly, we have a second vector here. Let's just call it B. B is 5 meters to the left. Okay, once again, writing the phrase to the left is somewhat redundant. Instead, we'll just think of that as the negative direction, such that B is equal to negative 5 meters. And then in part A of the problem now, to get the student's final position, what we want to do is add these two vectors together to get a third one. The sum, or also sometimes called the resultant. We'll call the resultant vector C, and that's going to equal A plus B. Now mathematically, of course, there's nothing to this. It's just 10 plus negative 5 for a total of plus 5 meters. But vectors are graphical quantities, and we should be able to add them together in that manner. In order to add the vectors together graphically, we employ a simple method. This is referred to as the tail to tip method of the vector addition. Here's how this little method works. Let's start with a number line like so. That's in terms of meters. Here's the origin, and then say 5, 10 to the right-hand side, and 5, 10 to the left-hand side, like so. And then the vector A here just goes from the origin, where the person starts, and then 10 meters to the right-hand side. So the vector A here on this number line simply looks like this. And then what I have to add to it is the vector B. And here's how we go about doing that. We take the tail of vector B and place it at the tip of vector A. Now this takes place on the number line itself, but I'll draw it below the number line such that you'll see it. I'm going to take the tail of vector B and place it here at the tip of vector A such that it looks like this. Once again, this is actually on the number line, but I'll just draw it below so you can see it. And then the resultant, the vector C, goes from the origin where we started this process to where we end up, over here, 5 meters to the right-hand side, like so. With a little bit of practice, you could actually very easily pantomime this tail-to-tip method of vector addition. It would look like this. You would have A plus B is equal to C. What's that? A plus B is equal to C. Okay, now let's take a look at part B of the problem. In part B of the problem, all that we're doing is reversing the order of addition. What is that basic property of addition called when you first learned it involving scalars way back when? Yeah, it's the commutative property. So let's see how that works here. Now for the commutative property, just reverse the order of addition to find the result C, which will now be thought of as B plus A. Mathematically, of course, it's the same thing as it is up at the top order. It's just plus 5 meters. But once again, we want to represent this graphically on the number line by using the tail-to-tip method of vector addition. Here's some. So here's our number line once again in terms of meters. Origin, 5, 10 to the right, 5, 10 to the left, like so. But now we begin, in this case, with the vector B, which remember from the top board is negative 5 meters. So the person walks 5 meters to the left like so. Right here is the vector B. And then what I have to do is take the tail of A and place it at the tip of B. So the vector A, I'll draw it below the number line so you can see it, is right here, like so. Notice that I've taken the tail of A placed it here at the tip of B. And then the resultant, C, goes from the origin where we started to where we end up, right over here, 5 meters to the right-hand side. Notice that the sum, C here, is exactly the same as it is up on the top board. So to pantomime this, it would just simply be B plus A is equal to C. So, lastly about this example before I move on, notice that it's perfectly fine to move vectors around in space. Notice, for example, vector A. It appears here on the bottom board, but it appears up here in this manner on the top board. That's perfectly fine as long as you maintain two things about the vector. Number one, you maintain its magnitude. This guy here has a magnitude of 10 meters. This guy here has a magnitude of 10 meters, and you maintain its direction. Points on the right-hand side, and points on the right-hand side, like so. Okay, next, still in one dimension, the next mathematical operation that's easiest to describe is the multiplication of a vector by a scalar. Not how you actually multiply vectors together. We'll get to that a little bit later on. But for now, very simply, multiplication of a vector by a scalar. Once again, in the one-dimensional case, this is trivial. Let's take a look briefly at another example. Now notice the notation that you see here on my Word document file. Notice that the vector is in bold type. That's exactly how you would see it, for example, in your textbook. In a one-dimensional case, as what we're examining here, this is very simple and straightforward. Okay, first of all, we're given that A is plus 5 meters, so on its own number line, we would see A, for example, like this. And then the first problem, all that we're going to do is increase its magnitude by a factor of 5. 5A is just equal to, obviously, plus 25 meters. So this vector is just 5 times as long as this one here, easy enough. Something like so. However, in part B of the example, when you multiply the vector by a negative number, by a negative scalar, not only do you change its magnitude, in this case from 5 to 15 meters, but when we pick up a negative sign, what does that mean about the vector negative 3a now?
It changes the direction.
Yeah, it changed the direction specifically by 180 degrees. So negative 3a obviously looks. Okay. So multiplying a vector together by a scalar is easy to do, especially in a one-dimensional case. It's literally nothing more than that. And now at this point, we start to move into two-dimensional cases. When it comes to two-dimensional vector addition, what was very easy in the one-dimensional case a few minutes ago, now it gets a little trickier. So let's take a look at that next. As you begin to copy down this problem, notice how the vectors are described. Two things, magnitude, and in this case, an angle to indicate direction. By definition, unless stated otherwise, the angle is with respect to the positive x-axis. Okay, let me begin to write this out as you're doing the same. We first of all have the magnitude of A as 5 meters. And then yes, with respect to the positive x-axis, it's going to form a 45-degree angle. B is a magnitude of 3 meters. With respect to the positive x-axis, it forms an angle of 135 degrees. Now, so far, the only means that I have available to me of finding the resultant, call it C, which is A plus B, is to use this graphical tail-to-tip method of division. Graphically, we use the tail-to-tip method. Now, when I did this in the one-dimensional case a few minutes ago, it was easy enough to do mathematically, such that all that I had to do was just kind of roughly sketch out the vectors on the number line. In a two-dimensional case, however, I have to be a little bit more careful. In a two-dimensional case, I'm going to measure all the distances by using a meter stick, and I'm going to measure all the angles by using a protractor. Now, obviously, you can't do that in your notes, but do sketch carefully as we go along. So I'm going to be really careful while doing this on a board. I'm going to use, first of all, my meter stick to construct the coordinate axis like so. Say something like this. Okay, then, my vector A, first of all, is at a 45-degree angle. So what I got to do is take out my protractor, center it right here like so at the origin, and then measure out 45 degrees, which is about right there. And then I have to draw a vector here. Vector A is 5 meters long. Obviously, I don't have enough board space to draw something that's 5 meters long, so I'm going to set up a little scale. I'm going to say that 10 centimeters here in my ruler corresponds to 1 meter in the problem. So my scale is that 10 centimeters equals 1 meter in the problem. So then therefore, what I'm going to have to do is draw a vector here that's 50 centimeters long. So to do that, do this nice and careful. Jenna, stay with me. I'm going to place my ruler like so, and then draw from, say, 10 to 60. Like so, and then right here is my vector A. And now, using the tail-to-tip method of vector addition, what I now have to do is I have to take the tail of B and place it here at the tip of A. So when I take my protractor, I have to center my protractor here at this location. And before I do, question?
The scale of 10 centimeters
Is 1 meter in the problem. So the problem is stated in terms of meters, but I certainly don't have enough board space here to draw a vector 5 meters long. So I'm just going to say on my meter stick that 10 centimeters on my meter stick is 1 meter in the problem, just so I can visualize it.
So it would be 50 centimeters.
Yes, so it's 50 centimeters long in terms of my scale. Okay, and I'll do the same thing with B in just a few moments. Okay, now with B, in order to get its direction, I position here the protractor like so, such that this is parallel to the x-axis, and then I measure out 135 degrees, which is about right there. And then what I have to do in this case is draw then this vector 30 centimeters long using that scale. So doing that appropriately. So, say from 50 to 20. Look about like that. And right here is the vector B. And now, using this tail-to-tip method of vector addition on my diagram, can anyone tell me how do I draw the vector C? From where to where? There.
Start from the origin,
That's
and
right.
then you connect the two to those vector B.
That's right. So it goes from here to here. So you would pantomime then the vector addition in the following way: A plus B is equal to C. Like so. And once again, doing this nice and careful with my ruler. That looks out like this. So here's my vector C. Now, how do I get the magnitude of this vector? How do I get the magnitude of the vector?
Is the diagram there?
Nope, I'm just gonna measure that. This comes out to be, hang on a second. This comes out to be about 60 centimeters. So when I measure it, I measure the magnitude here, C, to be 60 centimeters. So in terms of the scale, by the way, that's 6 meters. So, and then how do I get its direction? Measure it. Take out my protractor, measure over like so, about 77 degrees, I'd say. Like so, for its direction. Okay, now I was pretty careful in doing this graphically by using the tail-to-tip method of vector addition, but are these answers here precise? No, they're always measuring it. So how do I get a precise answer? That is, how do I measure analytically? how do I guess I should say, how do I obtain an answer? Analytical. There's a specific way and notation that goes along with doing this. I suspect that some of you may have seen at least parts of this notation before, but here's really where I begin to lay it out for you. In order to begin to describe how we add vectors together analytically, we have to define some terms. As I define these terms and then begin to work through this notation, for now, forget about the problem. We'll come back to that a little bit later. Let's begin this analytical process by first of all defining what is called a unit vector. The unit vector has the same properties as we've described thus far of ordinary vectors, except for two things. Number one, they always have a magnitude of 1. So for example, in the problem briefly, if we're talking about lengths in terms of meters, then the unit vector would have a magnitude of 1 meter. That's, by the way, what the word unit means. It means magnitude of 1. And then secondly, unit vectors always define specific directions. For example, there is a unit vector that defines for us specifically the positive x direction. Like so. This unit vector is given the following symbol. We first of all refer to it as a lowercase letter I, and then you'll see me draw this little symbol here above it in the following way. This is referred to as I hat. I hat is a unit vector in the positive x direction. The way that you'll see it on a Word document file or in a textbook, however, is once again in terms of bold type. Here's how you draw it on board. And then similarly, perpendicular to this, there is a unit vector like so that defines for us the positive y direction. This is referred to as j hat. I hat and j hat are the unit vectors that define x and y. If you're talking about a three-dimensional case, perpendicular like so in the z direction, the unit vector that is used to describe that is referred to as a hat. But suffice to say, in 2 dimensions, we have I hat and j hat. I'm sorry?
I'm going to read those.
A little bit. For now, we'll keep it simple, 2 dimensions. All right, now let's just say generically that I have a 2-dimensional vector in space. Once again, forget about the problem. We'll come back to that. So let's say that right here is just a vector in space A. And then, as we've already described, it has a magnitude in a direction like so associated. Any vector in 2-dimensional space, however, can be thought of as the addition of 2 other vectors. One vector that specifically points along the positive x-axis, like so, and another vector that specifically points along the positive y-axis, like so. These 2 vectors here in green are referred to as the components of A. The component of A in the x direction and the component of A in the y direction. And you then, therefore, very simply form a right triangle. Now on this right triangle, things are labeled in the following way. The size of this side of the triangle is called the component of A in the x direction. This is just labeled as a sub x. The size of this side of the triangle here, this is referred to as the component of A in the y direction. This is referred to as a sub y. Now finding those components is easy to do because it's just a little bit of right triangle trigonometry. For example, if you know the hypotenuse A is angle theta, what trigonometric ratio would you use to find the adjacent side of the triangle A sub x? Cosine of theta is equal to adjacent over hypotenuse. If you cross multiply a little bit, the adjacent side of hypotenuse multiplied by the cosine of the angle. And then similarly, if you know the hypotenuse A and the angle theta, what trig ratio would you use to find the opposite side of the triangle, A sub y?
Sine.
Sine. Sine of theta equals opposite over hypotenuse, like so. If you cross multiply a little bit, A sub y is equal to A sine theta. Of course, the process can be done backwards if necessary. For example, let's say that you already know a sub x and a sub y, what simple theorem would you use to find the magnitude of vector A? Pythagorean theorem. So, and then lastly, for the basics here, if you know a sub x and a sub y, what trig ratio would you use to find theta? Okay. So, now as I describe all of this, of course, there's nothing new here. This is just right triangle trigonometry. But it's right triangle trig now dressed up in its full vector notation. What vectors allow us to do is allows us to come up with the symbology that is necessary to link together algebra and geometry and trigonometry. You link the two together by using vector notation. Yeah.
What was the components of the vector that you used before?
Okay, so how do we write them, first of all? First thing we have to learn is how to write them. Okay, here's how we do this. Okay, the vector A in component form, as we say. Sometimes we say we resolve the vector into its components, or break the vector into its components. All of that means the same thing. We do this in the following way. This side of the triangle here has a magnitude of a sub x. So what is the vector itself? The vector itself here in green is the magnitude a sub x multiplied by the unit vector I hat. This guy right here now has a vector is a sub x I hat. And then similarly, this side of the triangle here, its size, its magnitude is a sub y. Well, what is the vector? Well, it's a sub y multiplied by the unit vector j. Writing a vector in this manner, as I said, is called resolving a vector into its components and breaking the vector into its components. And then Nathan, a couple of moments ago, asked me, okay, well, this is easy enough to do, but why bother doing it? Well, watch what happens now if you, now just generically, add two vectors together when they're in component form. So once again, forgetting about the problem, I'll come back to that in a few moments. Generically, let's just say that I add two vectors together. So here's an A, and here's a B, using tail to tip like so. And then before I sketch the result here, let's just look at these two vectors by themselves. So first of all, vector A. Vector A has a component right here, a sub x, and it has a component right here, a sub y. So in component form, as we say, A would be written as a sub x I hat plus a sub y j. Okay, similarly, take a look now at just vector B all by itself. Vector B all by itself has right here a b sub x, and right here a b sub y. So in component form, B is equal to b sub x I hat plus b sub y j. And then now we want to find the resultant, once again, vector C. Vector C is equal to A plus B. Using the tail to tip method of vector addition, on this diagram, obviously, we would then draw vector C like so. Here. Now just take a look at C there in green, all by itself. C, all by itself, has its own components. Right here in green is a C sub x, like so. Right here in green is a C sub y, like so. So just in component form, C by itself is C sub x I hat plus C sub y j. But, as I heard a couple of people gasp a few minutes ago, what is C sub x also happen to be equal? A sub x plus B sub x. What is C sub y also happen to be equal to? A sub y plus B sub y. So this is then how we analytically add vectors together. Break the vectors into their components like so, and then just add the components together to get your resultant. Now, as I was asking you guys on the top board a few moments ago how I start to add the vectors together, somebody in the back of the room says, well, something with right triangles. Yes, that's exactly what we're doing here. All that we're doing are adding sides of triangles together to get, in this case, the resultant. But we do so with a very specific symbology, and that's the symbology involving unit vectors that I'm describing here. So it's important that you learn that symbology because I'm going to be using it essentially from this point forward throughout the entire year. Now, getting back to our example here on the continuity. In order to analytically add the vectors together, what I have to do is I have to take the vectors A and B from the top board, break them into their components. So let's take a look at vector A from the top board just by itself. Okay, vector A has a magnitude of 5 meters, and then immediately I start picturing its components like so, where we're given that this angle here, remember, with respect to the positive x-axis, was a 45-degree angle. And now in component form, here's then how we write the vector A. So we first of all have right here a sub x, the adjacent side of the triangle. This is nothing more than the hypotenuse multiplied by the cosine of the angle. So this is 5 cosine of 45 half. And then right here, the opposite side of the triangle, this is a sub y, and that's just equal to the hypotenuse multiplied by the sine of the angle. So this is 5 times the sine of 45 degrees, change it, all in terms of meters. Get in the habit of listing the units as we go here in practice. Okay, now I'm just going to go ahead and calculate this out. Going down 2 decimal spaces is perfectly fine. 5 times the cosine of 45 degrees is about 3.54. So that's this guy right here. And then as you recall, hopefully, remember that cosine and sine of 45 are the same number. So the j hat component is also 3.54. So this side of this triangle is 3.54. This side right here is 3.54. And now we do the same thing with vector B. Take a look at B from the top board. So here's vector B. That looks like that. The magnitude is 3 meters. And then with respect to the positive x-axis, this angle right here is 135 degrees. And then I start picturing the components of the vector B. So, how do I get these components? How do I get, for example, right here, B sub x? Well, B sub x right here is once again just the adjacent side of the triangle. It's nothing more than the hypotenuse multiplied by the cosine of the angle. 3 times the cosine of 135. Okay, right here is the opposite side of the triangle, that's the B sub y. To get it, it's nothing more than hypotenuse times the sine of the angle. So, now as I did this, notice that I didn't make any assumptions about positive signs or negative signs. As long as you define the angle with respect to the positive x-axis, and then take cosine and sine of that, the negative signs will work themselves out. So for example, if I take 3 times the cosine of 135, I do in fact get a negative number. It's negative 2.12. So the B sub x right here pointing to the left is negative. That comes out by taking the cosine of this angle. Now, this guy here should be a positive. Let's see if it is. So 3 times the sine of 135. Sure enough, it's the same number. Positive, positive 2.12. So, and then lastly, we just add everything up here to get the result, to get the vector C. So vector C, which is A plus B, just in terms of its own components, would be C sub x I hat plus C sub y j. And in order to get those components, we just add them together. So the C sub x first is going to be A sub x, this 3.54, plus B sub x, this negative 2.12. 3.54 plus negative 2.12 works out to be 1.42. So, and then we get the C sub y by adding together A sub y, this 3.54 here, plus B sub y, this 2.12. So 3.54 plus 2.12 equals 5.66. Change it. Now into which quadrant does the vector C point? First quadrant, positive x component, positive y component. So therefore, the vector c, all by itself, looks something like this. So right here is the vector c. But what we have found analytically is that this side right here is 1.42 meters, and this side right here is 5.66 meters, like so. So then lastly now, to finish the problem and compare it with my measurements up on the top board, what do we do with those components to find the magnitude of the vector c? Right there. Okay, so let's see how close my answer is on the top board. So we've got 1.42 squared plus 5.66 squared, square of that junk, and then we're about 5.84. So, well, I was reasonably close up on the top board, of course, by measuring everything out, but this right here is a precise answer, minus a little bit of round off here. And then lastly here, Ryan, in order to get the angle, like so, called theta, using the two components, what do? How do I find theta using the components? And cosine, tangent, always do the components, not the hypotenuse, do the components. Tangent of theta is equal to opposite or adjacent. So inverse tangent of that ratio will compare it to my 77-degree angle on the top board. 6, 2, comes out to be about 76 degrees. So my measurement on the top board is pretty close, but these answers here are precise. Yes? The reason why you don't use the hypotenuse will be illustrated in my last example in just a few moments. Why you always use the components with an inverse tangent to get the angle. Let me illustrate with one last example. Now, when you add vectors together that are already in component form to get the resultant, then it literally just takes a few seconds to end up with your answer. Lastly, we'll take a look at this. Notice, by the way, the problem here, as you see it on this word file, that I hat, j hat, those unit vectors are in bold type. That's how you'll see it in the textbook as well. Okay, these guys here are dimensionless. It's just a math problem. Okay, now easy enough in this example. A is 5I hat plus 4J hat. B is negative 8I hat plus 2J hat. To get the resultant C, which is just A plus B, obviously all we do here is add the components together. So in the X direction is just 5 plus negative 8, so negative 3I hat. And then the J hat direction is 4 plus 2 for 6. So easy enough. Now into which quadrant, however, does the vector C point? Second one. Negative x and positive y component. It looks perhaps something like this. So right here is the vector C, where this side of the triangle here in the negative direction is 3, and this side of the triangle here in the positive direction is 6. Now once again, we can just use a little bit of Pythagorean theorem there to get the magnitude. When you square the negative 3, of course, the negative sign squares out. So this will be 6 squared, which is 36, plus 3 squared, which is 9, 45, take the square root of that using the Pythagorean theorem, you get about 6.7. But now you run into a small problem here briefly in order to find this angle theta right here, the direction that this vector makes with respect to the positive x-axis. If I find the tangent of theta as opposite over adjacent like so, and now here's where I'm beginning to illustrate why it's the components that are important. If I do the inverse tangent of that, I end up with the following on my calculator this way. I end up with theta as negative 63 degrees. Your calculator doesn't know the difference between second quadrant and fourth quadrant, but you do, and you have to be quadrant specific. The 63-degree angle that my calculator found is, of course, actually this angle right here. So what do I have to do to that negative 63 degrees on my calculator to get the angle theta in question? Add 180 to it. So, which will then give us 117 degrees. This. So your calculator doesn't know the difference between second and fourth quadrant. You do, and you have to be quadrant specific. Your calculator doesn't know the difference between first and third quadrant. You do, and you have to be quadrant specific. So by using the components, x and y, that then tells you what quadrant the vector is in, thereby allowing you to make an adjustment as is necessary to find the angle theta. Now, as I completed this problem here, notice that I didn't really even have to bother doing the tail-to-tip method of vector addition here, because everything was in component form to begin with, and then I just added it up. It was literally that easy to do. However, in component form, though, sketching out what occurs here in this problem is actually really simple and straightforward. Let me just briefly finish the tab. It's not necessary for me to measure out all of this stuff by using a ruler and a protractor. Just briefly sketching it here is good enough. So here's what the overall addition looks like in this example. Okay, first of all, from the top board, vector A. Into which quadrant does vector A point? First quadrant. It has a positive x component and a positive y component. So it's like over 5 and up 4. It kind of looks something like that. And then using the tail-to-tip method of vector addition, I have to place the tail of B to the tip of A. So I have to start by drawing from B right here. Now, into which quadrant does B point?
Second.
Second. Negative x and positive y. So it's like 8 in this direction and 2 up like so. Kind of looks something like that. And then therefore the resultant, vector C, is just right here in my diagram. Compare it to the vector that I drew up on the top board. It's the same thing. So pantomiming it, using the tail-to-tip method, it would just simply be A plus B is equal to C. No, you always go from where you start the process at the origin to where you end up. So you pantomime it like so. A plus B is equal to C. Okay, any questions? Okay, very good. Once again, just to reinforce, there's nothing new here, of course, but in vector symbology, drawn out in this manner, this is how you link together geometry and trig with algebra. That's the importance of vectors. All right, now at this point, we're going to go outside in just a moment here. Finally, we can look at the sun. So when we go outside in just a moment, what I want you to do is the following. I want you to kind of like line up against the railing, going in that direction. Once everybody is outside, then I'll explain what it is that you're going to see. Now, when you look through the eyepiece, which is right here, you're going to see, first of all, the background sky. It's not going to appear blue. It will appear black because you're blocking out most of the light. And then the sun itself will be an orange sphere. Now, when you look at the sun, look at the surface. You can see here, you're also going to form a triangle, 3 big sunspots. And each one of those sunspots, as I mentioned earlier, is larger than the Earth itself. Now, every so often, approximately every 3 or 4 people or so, I'm going to have to kind of go back in and readjust the telescope a little bit to put the sun back in the center. Because after a couple of minutes, the sun would actually move out of view. Now, why is that? Why would the sun move out of view? Because the Earth is rotating. And when you use then once you have seen the sun, then just go off to the side, because after everybody's had a chance to see the sun, you want to try for yourself a little bit of what is called digiscoping. Try to get a picture of the sun with the phone. I'll show you how to do that here in just a second. Otherwise, just go back inside. Okay, so, come on up. Sunbus? Yeah, you see some little black specks. You see them there on the surface of the sun? Yeah, so the black specks are not a dirty lens.
Yeah,
They're sunspots.
I would have.
No, they're sunspots. Sunspots?
Get my phone once I can just. So I think I have my phone.
So imagine Galileo doing this, at just the right moment, through the fog, going like that. That's stupid, don't do that. But he didn't steer his eye out. If he did it with a telescope, he'd go blind. Close your other eye. Okay, so do this. Close your other eye and relax. There you go. Okay, and then you see those black specks? It's not a dirty lens. Those are the sunspots. Those are the sunspots. It's larger than the Earth. Well, look there. They take some time. But the sun is like 800,000 miles above us. Now, when you look at those specks, it's larger than the Earth. This is a really good basic starter telescope. It's only very good. It's only very good. Your eyes don't see the light. It's like they're 3 times bigger than this. That's not like I mean, you look at these telescopes and the price we get. Type in, really, looks like that. And then it lines up and goes with the sky. Looks like you say, I want to see this. Yeah, you can. But I don't like it. I don't like it. I want to see this. This is picture, it's 6 inches. My biggest one is 20. Yeah, it's split. Little dots are bigger than the Earth.
Attention Valley students, attention Valley students and staff. The buses are not where they're supposed to be. All buses will be between the Mercer Hall and the gymnasium, by the gymnasium. So please, as you get out of your classrooms, proceed to that area to catch your respective buses. Again, please go catch your buses on the service road between the gymnasium and Mercer Hall. Thank you.
This is, by the way, considerably more powerful than Galileo's. Well,